thank you all for joining us today. This is the sixth talk for the third season for IGCP648 virtual seminar. So I'm Luc Doucet, I'm your host. Just want to say that last week we had a lot of fun with our epic earth science battle about plate tectonics. And if you want, you can check out the recorded video on our website. And I just put the links in the chat. So if you're interested. And it's pretty good that today we are having Professor Dietmar Müller, Professor of Geophysics at the Science School of Geoscience, University of Sydney, and he will present plate tectonics rules, absolute plate motion and plate mantle system evolution, which is a great follow-up for last week debate. So Dietmar, with his Earthbite research group, combines tectonics, geodynamics, and sedimentology to build virtual Earth models from a global to regional scale. So Dietmar, the audience is all yours.
Thanks for the introduction. It's a great pleasure to be here and give an IGCP648 talk, something that's been on my to-do list for a long time. So as you can see, what I'm going to talk about reflects a massive group effort by the Earthbite group and our collaborators, mostly ex-Earthbiters. And it's also worth noting that without support by the AuScope simulation and modeling infrastructure development and the NCI, we wouldn't be here. Okay, plate mantle system evolution. That's the topic of today's talk. So it's a key to understanding the deep carbon cycle, the evolution of complex life, and the formation of various types of ore deposits and many other Earth system phenomena. So, well, why are we devoting a talk to this issue? Well, one reason is that it's not that easy to model absolute plate motions in a mantle reference frame, which is the starting point for modeling the coupled plate mantle evolution. Relative plate motions are fairly well constrained, using oceanic, magnetic, and gravity data for post-Jurassic times, combined with geological data and paleomagnetic data. But absolute plate motions for the entire plate assemblage relative to the mantle is much more difficult to constrain, especially further back in time. So paleomagnetic data can be used to constrain paleolatitudes and are used to make true polar wonder corrections. And they're important as paleomagnetic poles reflect both the motion of the plates as well as the motion of the plate mantle system relative to the core, called true polar wonder. But of course, the problem is that we don't want to be modeling true polar wonder if we are interested in just understanding the plate mantle system. And so where do we go from here? So how do we isolate plate motions relative to the mantle? Right? Okay, so traditionally we start with paleomagnetic data. And we're all familiar with apparent polar wonder paths, and you don't have to be an astrologer to agree that they look a little like zodiacs. See, for example, Leo here on the lower left corner. And that's fine, but if we derive absolute plate motions from apparent polar wonder paths, they inherit these properties that I would call zodiac properties. So we have many abrupt changes of plate motion. And sometimes they're plausible and other times they're not geodynamically plausible because, of course, geodynamic rules are not built in to these sorts of reconstructions. Also, paleomag data provide poor longitudinal constraints and also have fairly uneven data coverage through time. Absolute plate motions have also been constrained by slab remnant mapping. So the upper figure here shows a P-wave velocity model at two different depths. Related to reconstructions at 140 and 240, at 120 and 240 million years ago. So these reconstructions are linked to the tomography by inferring slab sinking rates. One problem with these approaches is that once you get to the lowermost mantle, it becomes quite questionable to what extent you can interpret these blue areas, which are presumably the slab remnants, but to what extent you can interpret them as an ancient location of a subduction zone. In other words, that all that's happened is vertical sinking of slabs and nothing else. So I'll try to convince you later that other things happen at that depth in the mantle. Also, this method is only useful for the last 150 or 200 million years. Right? Now, plate motion speeds are strongly driven by slab suction and slab pull. Right? Now, slab suction and slab pull presently account for about 40 to 60% of the forces on plates. These forces change only when the network of plate boundaries changes substantially, for example, through ridge-trench collision, subduction initiation, or continental collision. And so the question is, how do we build these geological or geodynamic constraints into our plate models? Now, one solution for this problem that has been suggested in numerous papers is that we take our paleomagnetically constrained absolute plate model and in addition align reconstructed large igneous provinces and kimberlites with the edges of piles of seismically anomalous materials sitting on the core mantle boundary, because these are called low shear wave velocity provinces, the LLSVPs. And they are assumed to be stationary through a geological time. So on the left-hand side, you see a plate motion model from Matthews et al., and that incorporates the Paleozoic model, the late Paleozoic model by Domeyer and Torsvik. And so that's the kind of model that comes out of this. That also includes empirical true polar wonder corrections extracted from the paleomagnetic data. And, you know, we can watch this reconstruction and it looks okay, right? But I think we'll dig a little more deeply into whether it is actually okay or not, what comes out of this. So the first issue with this approach is that it has become quite obvious recently that LLSVPs are a seismic imaging artifact. So there was a nice paper by Davai and Romanovic in 2020 in Tectonics, and there were other papers before this one, for example, by Schubert et al. And Tkalcic et al. In 2015. They all came to similar conclusions, which is that if you combine seismic tomography models and also look at some fluid mechanic constraints, then it turns out that LLSVPs do not extend as compact uniform structures high above the core mantle boundary. Instead, they contain well-separated low-velocity conduits that are shown here, high above the core mantle boundary, and that extend through most of the lower mantle. And each LLSVP is composed of a bundle of thermochemical upwellings enriched in denser than average mantle. And it is only when the tomographic model is filtered to long wavelengths that the two bundles of plumes appear as uniform provinces. So the shape of LLSVPs is controlled by the distribution of subducted slabs, something that's been found in numerous independent geodynamic models, and the position of LLSVPs and upwelling dynamics should therefore be time dependent. The conclusion of the three papers that I've mentioned here, as well as of many others, is that LLSVPs as compact uniform structures do not exist and are obviously not stationary, and their present-day edges cannot be used as reference frame for the longitudinal position of plates. Now, that's not the only issue with the approach that I would call the traditional approach at this point. Let's look at mean plate speeds through time, and that's shown here on the left-hand side based on the model, the same plate model that I showed before, except for the colors now indicate absolute plate speed. On the right-hand side, we're looking at global versus continental root mean square speeds of the plates through time over the last 410 million years. Right? There's the RMS speed on the y-axis here. Right? And so what we see that plate speeds increase and increase back through time before 200 million years ago. And so we have to ask ourselves, well, is that reasonable? Do we expect the plates to go faster and faster back in time into the Paleozoic? The speeds might have been much faster in the Archean, granted, right? But I don't think there's much of a good rationale behind the plates speeding up into the mid-Paleozoic. So I think the answer is no. We have no reason to expect that plates should behave this way. Then there's a third issue. Let's have a look at net rotation through time. Net rotation is a rotation of the entire plate assemblage relative to the spin axis of the Earth through time. Several people have worked on this. For example, Thorsten Becker considered a global plate net rotation rate above 0.2 to 0.3 degrees per million years as geodynamically unreasonable in a geodynamic analysis in 2006. And that was followed by an analysis by Conrad and Bain, and they came to a very similar conclusion. They said 0.26 degrees per million years should be an upper limit for net rotation of the plates. So in contrast, in the model that I've just shown, which is generally not so badly behaved in post-Pangea times, when we have many more constraints than at earlier times, of course, you see the net rotation goes crazy at earlier times. So we have rates of up to 1.5 degrees per million year, right? Now, this is a problem because it's geodynamically implausible, and essentially it makes it impossible to build sensible plate mantle models using this approach. So how do we go about constructing an absolute plate motion model that is geodynamically plausible, right? Okay, net rotation, well, we don't want much of it, even though it's in our models. We want to aim for something less than 0.2 to 0.3 degrees per million years. Then let's look at trench behavior. So when it comes to slab rollback or slab advance, we want some of it, but not very much either. So our models tend to have crazy trench motions in the Paleozoic because as net rotation increases, of course, trench motion increases as well. Right? Then there was a seminal paper by Walter Schellert and others in Earth Science Reviews in 2008, where he demonstrated that most trenches roll back slowly, which makes geodynamic sense, and trench advance is extremely rare, and the mean rollback speed of trenches is about 1 to 2 centimeters per year. And so that's we take that as a rule that we want to build into our models combined with the net rotation rule. Okay, so first of all, in order to construct such a geodynamically plausible model, we need to build a plate model with evolving plate topologies, and a model that includes now subducted ocean floor. Of course, that is riddled with all sorts of issues, right? But first we had to build the technology to actually make that happen. And so we did that by developing G-plates in a direction that enables us to build connected networks of plate boundaries, and we call those continuously closing plate polygons in G-plates. And I'm sure there's a few people in the audience who have played around with this technology. And on the right-hand side, we see an example for how this works. Now, many of you would have seen our recent plate model for the last billion years. And I think that there's a few people in the audience who were co-authors of this effort, especially Alan Collins and his group. This was led by Andrew Meredith, who's now at Leeds, one of my ex-PhD students. And so in this animation, you can see initially the supercontinent Rodinia being assembled, then breaking apart, Gondwana forming, then Pangea, and so on. And you're all familiar with most of these model aspects. Now, this model is in the paleomagnetic reference frame, which is a useful starting point, and places the continents in appropriate latitudinal belts through time, but it's not useful to understand how plates and plate boundaries have moved relative to the mantle for all the reasons that I outlined before. So this brings us to the solution, which we call absolute plate model optimization. As this concept, based on tectonic and geodynamic criteria, was developed and introduced by Mike Tetley as part of his PhD at Sydney Uni, and it was published in JGR in 2019. And on the right-hand side, we outline the recipe for how this works. So for a given time, we start with the stage rotation pole of Africa, Africa being our mother plate at the top of our plate hierarchy relative to the spin axis. And this initial guess is of an absolute rotation pole, the stage pole, is calculated from global paleomagnetic data. Then we randomly perturb the starting rotation within a large radius of 60 degrees, and evaluate a cost function equal to the sum of 3 constraints. So we want to minimize global net rotation to the bounds that I mentioned before. We want to have trench migration dominated by slow rollback and limited to less than 3 centimeters per year. And we also limit the speed of the continents as a function of their size. Now, we build that in as an additional safeguard because we know that there's a speed limit for large continents. And so there was a nice EPSL paper some years ago that Sabin Zahirovic, I think, was also in the audience, wrote to demonstrate that the speed limit is an important criterion as well. And for relatively young times, less than 80 million years ago, we use hotspot tracks, and that we of course want to honor where we have them, but we do allow hotspots to move. And so now I'm going to show you, without going any further into the details of this methodology, what actually comes out of if we do this back through time. And so this is now a view of 1 billion years ago, which is quite different from the view that you're used to in paleomagnetically constrained reconstructions, because this is a reconstruction in a Mantle reference frame, right? So I'm going to show you an animation next that will model the continents and the plates, the motions in a Mantle reference frame through time, with continents shown in gray. The mid-ocean ridges are white lines, and subduction zones are the black toothed lines here. And the red colors, red, green, and bluish colors, represent the paleo-age of the ocean crust, using the color scale below. So when we're going to watch this, it's important to keep in mind that this reference frame is really different from a paleomagnetic reference frame, right? So one way to look at this is that each episode of true polar wonder that might have occurred since 1 billion years ago would have to be added back into these plate motions to obtain true paleolatitudes, right? Because we are only looking at the motion of the plates relative to the mantle here. And so we've tried to model them using sensible rules, right? Okay. And so, keep in mind the names of these various bits and pieces of Rodinia, as they're not going to be shown on the animation. So let's move ahead and actually look at this through time. So initially, this video shows a period of Rodinia stability, followed by breakup via the formation of the Alamastor Ocean, which is a proto-Atlantic Ocean basin that starts forming about 830 million years ago between Congo, Kalahari, and Amazonia cratons. So around 800 million years ago, we saw another rift forming the Proto-Pacific Ocean, separating Siberia and North America from North China, Australia, and Antarctica. Then after 600 million years ago, we'll see a third rifting event creating the Iapetus Ocean, separating Baltica from Amazonia and Laurentia. Then around 550, we saw Gondwana assembling, and now after 490, the ephemeral Iapetus Ocean is replaced by the Rheic Ocean, that ultimately closes again, leading to the assembly of Pangaea that we see here. And Pangaea ends up being stable for about 100 million years until breaking apart again. And so this approach here implicitly constrains both paleolatitude and the paleolongitude of plates in a Mantle reference frame without the need to assume stationary LLSVPs. Now let's have a look at how this model behaves in terms of our rules of tectonics and geodynamics. This graph shows the net rotation of our entire plate assemblage over time. So note the large fluctuations in net rotation implied by the model based on paleomagnetic data, which is our starting model in pink. And the optimized model is shown in blue here, and you can see immediately that it's kept within a range that is regarded as reasonable by geodynamicists, namely below 0.3 degrees per million year. Now let's have a look at trench motions. So again, we have time on the x-axis, and now we have the median value of trench orthogonal motion here on the y-axis, right? Where positive numbers represent trench rollback and negative numbers trench advance, right? And the colors show, again, the pink colors are the PMAG model, and the blue colors are our optimized model, right? And so you can see that the median trench motion is mostly confined between positive values of 0 and 2 centimeters per year in case of the blue model, because there are some outliers, right? You notice especially the large outlier between 410 and 440 million years ago, which is an artifact of the stitching of our post-410 MA model with earlier plate motions, which clearly needs future improvement here. So we are not able to get rid of this at the moment without actually changing the plate model. And so, yeah, so you notice that the unoptimized model, the pink one here, has significantly larger fluctuations in trench motion, including many periods of trench advance down here, right, which we regard as unreasonable because it should be rare. And it is much more rare in our blue model here. Okay, so now that we are reasonably happy with our initial version of a mantle reference frame, now let's start investigating how the mantle is stirred through time by the subduction history implied by our plate model. And so this geodynamic model has an initial slab depth of 1,200 kilometers. So we insert the slabs into the mantle to get it going, assuming that there's a previous subduction history prior to 1 billion years ago, that is. And we have an initial basal layer thickness of about 100 plus kilometers with 3% excess density. So that's the layer that will ultimately be molded into LLSVPs. So running our mantle convection model forward illustrates an initial model warm-up phase, roughly from 1,000 to 800 million years ago. You see that here now. And during this time, the mantle is gradually populated with slab material. And so the plot on the right is a cross-section, an equatorial cross-section through this model. Right? And so the large red pile you see as forming on the lower left is the Pacific LLSVP, whereas the African LLSVP is on the other side. Right? So it's nice to watch the map view and the cross-section at the same time. And you notice the dotted line here, and that's the boundary between the upper and the lower mantle. You notice a large difference between slabs subducted along slowly moving versus fast moving trenches in terms of the geometry of slabs passing from the upper to the lower mantle. The initially homogeneous basal layer, which in our model is less viscous but slightly more dense than the overlying mantle, is gradually being segmented and displaced by slab material reaching the core mantle boundary, creating piles of material which are synonymous with our paleo-LLSVPs. And you'll notice that negatively buoyant slab material spreads out on the core mantle boundary and pushes and deforms these paleo-LLSVPs much along the lines as proposed by many geodynamicists and seismologists, and in turn initiating mantle plumes. You'll also notice that the Pacific LLSVP down here forms much earlier than the African LLSVP. And that's simply because the Pacific region has been largely isolated from subduction for the last 600 million years, while the same does not hold for the region around Africa, which has only been subduction free for about half that time. So now let's have a look at a 3D view of mantle convection through time from a Pacific perspective. So these views were prepared by Omer Baudur, one of our ex-PhD students who's now working with Nico Flamand. So this is the Pacific perspective here, and after an initial phase of model warm-up before 800 million years ago, we see a proto-Pacific paleo-LLSVP emerging that initially forms a ring-like structure but becomes more consolidated after 600 million years ago. And after reaching the lowermost mantle, subducted slabs move laterally towards upwelling regions. Cold and stiff slabs push the hot, low viscosity basal structures to form steep ridges, which you can see very nicely in this visualization. And these are the ridges that then form paleo-LLSVP margins, but they can also form within LLSVPs. And of course, it's these thermochemical ridges where plumes ultimately form, and they tend to be pushed to migrate towards the interior of the basal structures, while the initially very steep ridges then become smoother. Our model also suggests that heated slabs may rise up from the core mantle boundary and climb over the edge of hot basal mantle structures, pushing the shallower part towards the interior of the basal structures. So you can see that as these blue tongues of material that are being pushed over these LLSVPs. Now let's look at the same animation without the slabs being in the way. So we've taken the slabs out, and so we can now see a little more clearly how paleo-LLSVPs evolve in this model. Plumes mostly rise from thermochemical ridges, especially those with a height of more than 1,000 kilometers. And our model predicts that plumes originating from these ridges can migrate within the basal structures as a whole or into the interior. And the plumes are largely vertical due to low viscosity and large velocities of the plume material, but sometimes show some tilting due to fast plate motion and induced subhorizontal flow. Right? And I should add that there's a striking resemblance of the general geometry of our modeled basal mantle structures with a tomographic model that was presented recently by Davai and Romanovich in their paper in Tectonics. Now let's look at the other side of the world. We'll look at the African hemisphere here, and so you can make out the shapes of the continents overlain in light gray with white boundaries. So the mantle in this hemisphere is dissected by multiple generations of subduction zones that are related to the successive closure of the Iapetus, Rheic, and other ocean basins in the Paleozoic. So that's what makes this hemisphere really different. Like in particular, Laurussia or Gondwana convergence that led to the assembly of Pangaea caused the segmentation of the basal structure of this region, which we'll see a little better in the next slide where we've taken the slabs away. So only long after the assembly of Pangaea does the African LLSVP emerge, similar to what it is today. Its basic geometry can be seen beforehand, but it's not as contiguous and connected at earlier times. So here we have the same thing now without the slabs being in the way. And so now we can see that the basal structures in this hemisphere remain much more dissected than in the Pacific hemisphere for a much longer time. This being a consequence of Laurussia-Gondwana convergence and all the subducted slabs that are being inserted into the deep mantle. And so we've seen here that the present day LLSVP underneath Africa and stretching all the way up to Iceland forms relatively late in the game here relative to the Pacific. Okay, I want to change tech now, and I want to briefly talk about what's the use of all of this. You know, somebody might say, "Well, that's all very nice. You know, modeling the plate mantle system. That's surely a purely academic endeavor. You know, and as geoscience comes under attack more and more, and losing students and losing the capacity for education in geology and geophysics, what is this all good for? Does it have any practical applications?" Right? Some of you might have seen this article in Geo Down Under. It's a brilliant website that was initiated by Louis Moraci at ANU. And so there are a few people who banded together outlining what all the issues are that we are facing at the moment, right? And there are many answers, many possible answers to this question, you know, what we should be doing to, you know, counteract this development, right? But one of them is to do with the green economy and mineral exploration and mining, right? So this is now an old article from over a year ago in the Australian, where it was predicted that mining would be ground zero of the nation's recovery post-COVID. And guess what? That's exactly what happened, right? Because the move to net zero inevitably means more mining. And this is an article that was recently written up in the BBC News, right? So now how do we make a connection between looking for metal deposits and modeling the plate mantle system? So here's a figure from a recent paper in Nature Geoscience by Hoggart and et al. That shows the global distribution of sediment-hosted metal deposits overlain over lithospheric thickness, illustrating that they often occur along craton edges. And so the cratons are the blue blobs in this map, right? And you can see that quite clearly here, right? And the conclusion of their paper was that 85% of sediment-hosted base metals, including all giant deposits, occur within 200 kilometers of these lithospheric boundaries. Now, okay, so that's very nice, but we still then need to understand, well, exactly where and at what times do metal deposits form along these boundaries. Now, that is not something that is currently known, right? Now, one idea is that rifting in the setting leads to subsidence and lower basal heat flow, enlarging the depth extent of hydrothermal circulation available for forming giant deposits. But what drives where and when these deposits form? Now, I'm not going to provide the answer today. I just want to provide a glimpse into the sorts of things that plate mantle models might enable us to do in the future. So this is again a mantle convection model and that was run by Chinchi Kao, and the video was created by Ben Mather. And so what we are looking at here is the vertical mantle convection velocity component in the mid-upper mantle with sediment-hosted base metal deposits overlaying. Right? And so we can use this association to explore whether there's a connection between upper mantle upwellings or downwellings and base metal formation in rifts along craton edges. Right? Now, if we do that, and so Ben has created these two plots where we see the upwelling or downwelling velocity. Negative upwelling velocity is downwelling here, right? On the x-axis, and the total mass of contained metal as a function of this quantity shown as a cumulative distribution graph, right? And there's a few things that you can see right away. So subduction-related copper porphyry deposits, that's the brown curve here, right? So they're clearly associated with negative velocities here, well, because they're associated with subduction zones and downwelling, right? Now, all the intraplate deposits, the ones described in the Hoggart et al. Paper, they're more clustered around zero, which is not a big surprise because there are neither major upwellings nor downwellings within the interior of continents. But if we take a closer look at this area that's outlined with the red dashed line here and blow this up, then we see, if we look at sediment-hosted copper deposits, but they tend to be associated with mild mantle upwellings, right? Now, there's perhaps some interesting clues in here that can be exploited together with a host of other data that we won't explore today, right? I also want to point out that just 4 days ago, we published a paper in our geology reviews that looks at the subduction part of this story, where we predict the emplacement of Cordilleran porphyry copper systems using a spatial temporal machine learning model. And that's the work of my recently finished master's student, Julian Diaz-Rodriguez, and also involves Rohit Chandra from UNSW on the machine learning side. You might want to have a look at this. So all the work that I've shown today is based on open source software, including work with our industry partners. Open access resources are critical for scientists from different domains to work together to tackle the important challenges and big questions of our time, including the survival of geoscience. In a post-COVID world, in challenging economic circumstances, open source software will be a low-cost way of doing research by everyone, industry, government, and universities alike. And it's also critical for the education of future scientists, right? And so my conclusions are as follows. Plate model optimization allows the use of geodynamic and tectonic rules to design a mantle reference frame. This avoids bad plate behavior, like excessive plate speeds, unreasonable net rotation, and excess subduction zone migration rates. Latitude and longitude are both constrained in a mantle reference frame. Plate, mantle, and tomography models converge. Now, this is really good news that seismologists and geodynamicists and tectonicists can actually agree that geodynamically modeled deep mantle structures looks just like what seismologists see. And that means that LLSVPs are composed of bundles of thermochemical upwellings. And the shape of these LLSVPs is controlled by subduction history, and the position of LLSVPs and upwelling dynamics are time dependent quite clearly. And plate mantle models will likely play a useful role for the next generation spatial temporal data analysis efforts in mineral exploration. So this is my last slide. None of this work would have been possible without the awesome Earthbite group. And it especially wouldn't have been possible without the long-term support by the RScope simulation and modeling group as part of the National Collaborative Research Infrastructure. And our geodynamic modeling wouldn't be possible without our brilliant national computational infrastructure. Thank you.